Welcome to The Explainer. Today, we're diving into something that feels like it's pulled straight from a sci-fi movie, but is happening in research labs right now: the future of AI in medicine. And we're going to tackle one big question: just how close are we to having a real-life Baymax?
I mean, really think about that for a second. Could an AI be your next doctor? It's a wild thought, but it's the very question researchers are trying to answer. So, let's dig in and see just how far we have to go before that's a reality.
To really wrap our heads around the future of medical AI, it helps to start with a familiar face. Baymax, from Big Hero 6. He's not just a cute, inflatable robot. He's actually the perfect symbol for the ultimate goal here: a true, personal healthcare companion.
That's the vision that's driving all this research, right? An AI that's not just smart, but empathetic. Something that knows everything about medicine, but is also available for you 24/7. And chasing that dream leads scientists to ask one very specific question.
And this isn't just a fun, catchy way to talk about it. A huge survey of over 60 different studies literally used this exact question to frame the entire state of medical AI research. It has become the benchmark, the gold standard, for where all this technology is trying to go.
All right, so how do we actually build a Baymax? Well, the journey starts by understanding that we don't need a generalist, we need a specialist.
The key here is the difference between a normal large language model, or LLM, and an LLM-based agent. You can think of a regular LLM as a brilliant med student. It's read every textbook, it can answer any question you throw at it. But an LLM-based agent, now that's the graduated specialist. It doesn't just know things, it can plan, it can reason, and most importantly, it can use tools to get things done.
And that's the fundamental difference. An agent isn't just a chatbot that gives you information. No, it's designed to be an autonomous system. It can perceive a situation, say a patient's symptoms, and then actually take action, using its memory and connecting to external tools like medical databases or your electronic health records.
So how do you make one? Well, researchers have come up with a core architecture. First, you give it a profile, which is basically its job description. Is it a diagnostician, a surgeon's assistant? Then it has a planning module to break down a huge medical problem into small, manageable steps. After that comes reasoning, where it uses logic to think through those steps. And finally, and this is crucial, it has access to external tools. Real-world data from medical records, imaging software, you name it. Okay, so you've got the blueprint for the agent. Now you have to actually train it to think like a doctor. And right now, there are basically two competing schools of thought on the best way to do that. On one side, you've got a method called fine-tuning. This is kind of like sending the AI to a super intensive medical school. You feed it specialized medical data over and over until it learns the ropes. On the other side, you have a method called retrieval augmented generation, or RAG. This is totally different. It's like giving the AI a permanent open book exam where it can look up the most current information from a massive knowledge base whenever it needs to. So, which way is better, med school or the open book exam? Well, a recent study decided to find out. They took 5 different AI models and put them through the ringer using MedQuad, which is this huge data set of almost 50,000 medical questions and answers. And the results? Well, they weren't even close. Just look at this one example with the LLMA 3/1 model. When they used the fine-tuning method, the med school approach, its performance score was a pretty dismal 0.025. But when they switched to RAG, the open book method, the score jumped all the way to 0.163. That's not just a little better, that's a massive leap in performance. And they saw the same pattern across almost all the models they tested. So the researchers' conclusion was pretty clear: RAG just works better. But what's really, really critical here, especially in a field like medicine, is why. See, medicine is changing every single day. New studies, new treatments, it's impossible to keep up. RAG allows an AI to tap into the very latest information in real time. It doesn't have to be completely retrained every few months, which is a game changer. Okay, so RAG seems like a huge step in the right direction. But before we get too excited, we need a serious dose of reality. As promising as all this sounds, this technology is nowhere near ready for your doctor's office. And researchers are very upfront about the major roadblocks that are still in the way. And we're talking about some major problems here. First up is the issue of hallucinations. That's the terrifying phenomenon where an AI just makes stuff up and states it with complete confidence. In medicine, that's a catastrophic failure. Then you've got huge issues like algorithmic bias, privacy, and security. And finally, there's the simple, boring but incredibly difficult problem of just getting these cutting-edge systems to work with the ancient, complex IT systems that most hospitals are still running on.
So, after looking at the dream, the architecture, the training, and the challenges, let's circle all the way back to where we started. It's time for the final diagnosis. How far are we really from Baymax?
The verdict is in, and we're not there yet. Not even close, to be honest. But, and this is a really big but, the exciting part is that we finally have a blueprint. The basic architecture for these agents is designed, and a really promising training method, RAG, is leading the way. For the first time, the path forward is actually becoming clear.
And when you look ahead, the opportunities are just incredible. We're talking about so much more than a diagnostic chatbot. Think about AI agents being integrated into physical nursing robots, or helping guide a surgeon's hands. Imagine training these agents in completely simulated AI hospitals, running them through millions of patient scenarios to make them perfect. The potential here is absolutely transformative. And that really leaves us with one last big question. As this technology gets better and better, and it's moving incredibly fast, the final hurdle might not be a technical one at all. It might be a human one. The question is, will we be ready to trust an AI with something as deeply personal as our health? And will that moment come sooner than any of us think?